This is a video for AQA Further Pure, second order differential equations 3, modelling with second order differential equations, 3.4, solving simultaneous differential equations. Let's have a look at this example then. Here I've got a pair of differential equations. One involves dx by dt and y and x, and the other involves dy by dt and y and x. So I've got two dependent variables. They are x and y. And I've got one independent variable, which is t. And as you can see, my derivatives are both with respect to t. These two equations are related, and they will need to be solved simultaneously. And we'll look at a technique for solving equations like this in a moment. Where might these have come from? Well, there are a number of physical situations that will give rise to equations like this. It might be something to do with a chemical process. So we might be looking at the production or take-up of two different types of chemical. It might be, and this is very common, a predator-prey type relationship, where we have got two species. In this example, for instance, we might have that x relates to the number of foxes in a particular population and y relates to the number of rabbits. Let's have a closer look at some predator-prey equations. In this example, we've got two assumptions. One, that predators increase at a rate proportional to the number of prey available, and two, that the prey increase at a rate proportional to their number, but also are killed at a rate proportional to the number of predators. So if we say that x is the number of foxes and y is the number of rabbits, then we would have something like dx by dt, so that's the rate of increase of predators, is equal to alpha y, where alpha is some constant. And if we have a look at the second assumption, we're going to have dy by dt is equal to, well, they increase at a rate proportional to their number, so that's going to be some multiple of y, but they're killed at a rate proportional to the number of predators, so that's minus some multiple of x. And these constants, alpha, beta and gamma, I'm going to assume are all greater than 0. There's that written up a little bit more neatly, just so that you can follow what's been done. So there's the rate of increase of predators, so that's these, that's the rate of increase of predators, is some constant times the number of rabbits, and here the prey increase at a rate proportional to how many prey you've got minus something to do with the number of predators on. So let's have a look at this example. I've got this pair of simultaneous differential equations, and I'm going to take the second equation over here and just rearrange that to give me that x is equal to y minus dy by dt. And if I differentiate that with respect to t, I'm going to get dx by dt is equal to dy by dt minus d2y by dt squared. And so now if I take this expression for x and substitute into here, and this expression for dx by dt and substitute into here, I'll have something that only involves y and t. So if we substitute into 1, we're going to get dx by dt is dy by dt minus d2y by dt squared, and that's going to be equal to x, which is y minus dy by dt minus y. And if we rearrange that now, I'm going to get d2y by dt squared minus 2 dy by dt is equal to 0. And so now I've got a second order differential equation in y and t only. There's that written up neatly. This is the rearrangement of equation 2, and then differentiate it, substitute all of that back into equation 1 and tidy up, and we get this differential equation to try and solve. So continuing with this example from this differential equation, the first thing we need is the auxiliary equation. So my auxiliary equation for this is going to be lambda squared minus 2 lambda is equal to 0. And that gives me two values for lambda. Lambda is equal to 0, or lambda is equal to 2. And so my general solution for this is y is equal to a e to the 0t plus b e to the 2t. Now we know that this is just going to be 1, so this is in fact going to be y is equal to a plus b e to the 2t. Now having got an expression for y, I can get an expression then for dy by dt, which is just 2b e to the 2t. Then if I think about equation 2 up here, from that I'm going to get 2b e to the 2t is equal to minus x plus a plus b e to the 2t. And rearranging that gives me x equals a minus b e to the 2t. And so my solutions are x is equal to a minus b e to the 2t, and y equals a plus b e to the 2t. And again, there's that constructed neatly for you. There's the solution of my auxiliary equation. There's establishing a solution for y from the auxiliary equation, and therefore for dy by dt, and substituting all of those back into actually a rearrangement of equation 2 here to give me x, and therefore my two solutions x and y. So in summary then, if we've got a system of differential equations and they could be of this form, where we've got dx by dt is some multiple of x plus some multiple of y plus some function of t. We haven't looked at an example with that, but it can be that complex, and a similar sort of expression for dy by dt. So in that situation, x and y are the dependent variables and t is the independent variable. And the system of equations can be solved by differentiating one of the equations and substituting into the other. So you do a rearrangement of one of the equations, differentiate, substitute into the other, and you should get a single equation which can then be solved to give you x and y as functions of t. The next video in this sequence is 3.5, Finding Particular Solutions.